Okay, we're on the second day in Chapter 8 on exponential functions, and we are just looking at this. You don't need to write this down, but this is day 2, 8.6. We're mostly talking about decay today, but I want you to take a look and tell me if you can recognize the difference between an exponential function and a linear. So let's just really quickly look at the tables without graphing. Aaliyah, look here. Without graphing, look at this. Do we see a pattern in the domain of this one? Number 1? Yes. We have an increase of 1. So we are looking now for the pattern in the range. And is this exponential?
Yes.
Yes. And what is the factor that is repeatedly being multiplied? 4. Times 4. Who can write the equation for this? Jack.
I think it's y equals 8.
Good job, you found that. 8 times
4 to the x.
Excellent. Good. Look at number 4. We're looking at number 4 now. Is this exponential, yes or no?
Yes.
Good. Can you write the equation, Tom?
Y equals 10 times 1/5 to the x.
I'm out of calibration, but it's working. It's almost working to the x. It says 1/5 to the x. Okay, it's slightly out of calibration, but excellent. So he sees the a value here, and 10 times 1/5 equals 2. Or he might, did you see it as divided by 5?
Yeah.
Divided by 5?
Yeah.
We don't have divided by 5 as a factor, right? So we change that to multiplying by 1 over 5, which is the same as dividing by 5. So the b in that case is 1/5. Looking at number 5. Looking at number 5. Is this exponential growth or decay?
Okay.
Exponential decay. Good. Matthew, what is the equation?
Y equals 2 times 1/3 of the x.
And so he found that the constant here, the constant factor is multiplying by 1/3. Or did you find divided by 3?
I did down 1/3.
It looks like we're dividing by 3, which is the same as multiplying by 1/3. And then here is the a value. Okay. Number 6. Do we see exponential growth or decay?
Neither.
No. What do we see, Madeline? Linear. How do you know?
Because it's not multiplying.
What are we doing here between these values?
Plus 4.
We're adding what?
4. Wait, no. Wait, yeah.
Adding 4, adding 4, adding 4. When you see constant addition, it's linear. And so everyone, the model for a linear equation?
Y equals x equals b.
And where does the 4 go? Is it the m or is it the b? Good job. It's 4x plus, what's the y-intercept?
-7.
-7. Good. Excellent. Y equals 4x minus 7. Okay? So as the year goes by, when you're given random tables, you're looking for patterns, and then you're hopefully able to write equations. Okay? Looking at these tables, you don't need to write this again. Just look at this. I have a big set. I took a couple of pictures from the book. This big set and this big set. So we've got A and B. Please don't say it. But one of these represents growth, one represents decay. So, which one represents growth? Is it A or B? 3, 2, 1.
B.
Now the thing that might be slowing people up is that we have fractions in both. But B does represent growth. So even though these are fractions down here, and the decimals are fractions as well, how are these fractions different than the fractions that we see in A, which are all decay? Sabrina. Good job. They're improper, which means they're all greater value than 1. So with a greater value than 1, you have growth. And with values between what? Here. Good job. 0 and 1, we have decay rather than growth. Okay? Good. So we are going to, we're going to do something here. Just a second. Let me stop the video. Okay, we're going to summarize what we've been talking about today. First, we didn't put this definition, the definition of exponential decay, down on Friday, so let's do it today. Exponential decay uses the same model as exponential growth. But as we just said, the b is a value between 0 and 1, or what I like to call a proper fraction, not an improper one, right? A values must be greater than 0. This was true for exponential growth as well. The a values must be greater than 0. Why must the a values be greater than 0? This is not something they really go deeply into. They just throw this into your rule for each of these. So I'm going to do a quick sketch here of, 4 possible exponential functions. Just a quick sketch. Yes. So we're going to have A, B, C, and D. So the first one I'm going to show is this. And then we have this. And then we might have this. And then we might have this. So, and I'm a little off calibration today, but we see the 4 possible exponential functions that we have graphed to date, right? There they are, going every which way. Now, only one of these represents exponential growth. Is it A, B, C, or D? The answer is A. Good. This is the only one that represents growth. What might another person say could represent growth as well if you didn't know the definition?
B.
C, that's right, C, because look, as the x values are increasing, this one appears to be increasing in the y values as well, right? But the definition of exponential growth is the a must be greater than 0 or positive. The y values end up all being positive. We don't have these reflections that you see down here. This is actually a reflection of B, isn't it? Okay, so which one of these graphs represents exponential decay? The answer is B, and only B. Even though D looks like it's going down, down decay, it seems to be a synonym, the A values are negative, so this is a reflection of actually A. So this one is exponential growth, and this one is exponential decay. And that question was on my daughter's Algebra 2 test last week, and a lot of people got it wrong because they thought this was growth, right? So they included this C with A, and this one appears like a decay, right? So this is an Algebra 2 question that maybe you'll remember, maybe. We'll see. Okay, we're going to summarize our exponential growth and decay with their rules both together right here. So classify and write the rules for functions of exponential growth and decay. Okay, so what is the model equation for exponential growth? Okay. Good. AB to the x. A times B to the x. And now, what about A? I just said it in this sample over here. What must A be? How do we write that? Good. A must be positive or greater than 0 for it to be called exponential growth. And then what about the B value? For growth, you just saw that in those tables. All the B's for growth have to be values that are what, Matthew? Greater than, B values must be greater than 1 or greater than 0. So 1/2, would that be growth? A B value of 1/2? No, he's right, it's greater than 1. And that's because if you have a B value, remember that's a proper fraction, or like 1/2, 1/3, 2/10, whatever, then you have this, which is decay. But what is the model equation for decay? Y equals, same thing, good. I hear 2 people saying it. It is the same equation, people. There is only one model equation we're using for exponential growth, and it's the same one for decay. When we use our growth factors, like on Friday we used a growth factor, or it was a decay factor, 1 minus R, 1 plus R, that is the B, okay? Otherwise, it's the same equation. We might plug in T instead of X, right? but it is an input. So it is the same equation. This is it. This is a whole chapter equation. That's it. Okay? But in this case, again, the A values must be greater than 0. Again, if it's really decay. And the B values now, somebody else. Somebody else. The B values must be what, Johnny? Less than 1, can it be negative? Greater than 0. Right, it's got to be some little fraction that's greater than 0, less than 1. Remember, they can't be equal to 1. What happens to the equation if B equals 1? It becomes a line, linear. It becomes just a horizontal line. Y equals some number. Okay? Good. So, what happens with our negative B? We kind of did a little sample of this earlier in the chapter to look at it, but go ahead and try it. Let's do 5 values, and let's try graphing this. Okay, when you plug in 0, you get 1. When you plug in 1, you have negative 2. When you plug in 2, you have negative 2 times negative 2, which is 4. When you plug in the negative exponents, you end up with reciprocals, right? So you end up with negative half or 1/4. So when we graph these, have you done that? When we plug in 0, we get 1. Filter. Okay, so when we plot these points on the graph, does this look like exponential growth or decay? You might think growth because 2 is a value greater than 1, but if we were to attempt to connect these lines, it looks like a zigzag, doesn't it? And actually, you would never even get a value of 0. So I'm leaving a little gap where the x-axis is, because what exponent could possibly make this turn into 0? I mean, an exponent of 0 causes the value of y to equal 1. A negative exponent gives us these kinds of fractions, right? Reciprocals. A positive exponent is giving us these kinds of exponential numbers, right? But we'll never have 0. So you can see why this is not growth and decay, and why a negative may not exist as the base for an exponential function. It doesn't give us an exponential function. So it kind of confines our domain, or I'm sorry, it confines our base, I guess you would say, to the values that we put in our rule. Okay? Does this represent exponential growth or decay? Okay, write the equation. Okay, so if you don't have it by just looking at this graph, we were given 2 points, right? So the first thing you want to do maybe is to put those into a table. We have 0, 2, we have 1, 4. So do we see a pattern? We know it's exponential. Look at the graph. You have a curve. You know what it is, so we can use our model. We're just looking for B and for A. And so we can look at the Y value change to find our B. What are we multiplying by? 2. So there's your B, and then we see our A right here, right? So Y equals 2 times 2 to the X. Good. Okay, let's see if you can do this next one without drawing it. Okay, thumbs up when you have it. Okay, so once again, you see it and you know this is exponential. Look at that. So it's going to follow the model because they all follow this model. So we see this point and this point. They are within 1 of each other in the X, right? From negative 1 to 0 is 1. So going from 4 to 2, what would I multiply by? 1/2. So we can write that as 1/2 or even 0.5, right? And then all we need to do is find our A, which is
2.
The y-intercept 2. Good. So when you plug in 0 for x, when you plug in 0 here, this becomes 1, and 1 times 2 is 2. So there's your equation. Good. The other way you might receive this question is, here is a word problem. There are 2 points in it. But notice in the first sentence, the graph of an exponential function. So now in your mind, you say y equals AB to the X, because it says it here. And you have 2 points. Could you make a table? And then find those A and B. And pause the video if you want to check your answer. Model for exponential decay looks just like growth.